So the idea with this is when we give you a graph and an integral, the idea is you're connecting with the fact that the integral of the function f of x dx. So if I have the graph of f of x, the integral is actually represented by the area underneath the curve. And then we have our lower bounds to our upper bounds. And I'm going to approach this, by the way, if this was a problem you were doing on an AP test, it would most likely be multiple choice, which means I would not show much work for this. I would just calculate the areas and then look for the answer. What I'm going to do though is I'm going to actually kind of represent how we can think of this in terms of the properties that we're going to be talking about over the next couple days anyways. So if I start at -3 and I go all the way to 2, you'll notice that this area is divided up into two different pieces or two different shapes. And what you want to do then is you want to find the area first from -3 to 0. So that's the area of this triangle down below. And because it's below the x-axis, we know that this area is going to be negative. So what I would like to do is think of this as the integral from -3 to 0 of the same function f of x, right? And then we also we have to go all the way to 2. So I have to end at 2, but that means I have a new area that's above the x-axis. And we know that this area above the x-axis, that's going to be positive, but it goes from 0 to 2. So notice my bounds are still going all the way from -3 to 2, except we're broken down by, or we're broken apart by x equals 0, because that's a nice friendly divide. And then all you can do is find the area. So if I look, I've got a base of 1, 2, 3. Now, notice I'm starting here at -3 and I'm going all the way to 0. So that's a +3. And then I go down 1, 2, 3, 4. So I'm thinking of that as a -4. And if I'm doing the area of a triangle, it's 1/2 base of 3, height of -4. And when I multiply that together, I end up with -6. So the area for this piece is -6. And then we're going to take and add that to the area of the blue piece, which is just a trapezoid. Now you could do this, you could break it down into a triangle and then add the rectangle, or this is a trapezoid that's kind of flipped over on its side. So if I think of it, here's base 1, that's a width of 2. Up top, base 2 is equal to 1. And then the height is 1, 2, 3, 4. So this would be 1/2 base 1 plus base 2 times the height. And 3 times 4 is 12. Half of 12 is 6. So I end up with a -6 and a +6 being added together. So my net area is equal to 0. All right, so that's the first one. The next one says, now calculate the area from 4 to -3. And you have to be very careful with this. This one actually ends up tricking a handful of people. Look at the bounds. We start with the upper bound. So I'm starting at 4. And then they're saying, go all the way to -3. Well, in this case, we're going the opposite direction. I don't like to calculate that way. So what we're going to do is we're actually going to introduce a property here that we talked about the other day. We're still going to take the integral of f of x dx. But if your bounds are flipped, so if I put the -3 down here and the 4 up here, because then we calculate from left to right, which is what we're used to doing, we just know that our answer is going to be opposite of that. So, and it's that same work. Now we got to calculate the area from -3 all the way to 4. Well, we already did the area from -3 to 0, right? We did that up here, and that was -6. I'm not going to show that work. You can kind of split that up. And then we did this area right here from 0 to 2, and that was a +6. So the only thing that's left over is this rectangle right here. And you can either count this as a 4 by 2, or you can just count 1, 2, 3, 4, 5, 6, 7, 8, since we know those are whole squares. So if I add this up, we know that the net area between the original two was 0. And what's left over is -8. So that negative makes it the opposite sign. And you just have to be careful. That's what happens when the bounds are flipped. When the bounds are flipped, it becomes the opposite sign. All right, and then the last one, I just threw it out there. We didn't talk about this, and I was really curious to see how you would approach this. So please, please, please make note that this absolute value bar stands for something important, and let's think about what that means. Absolute value of just a regular number means that everything is positive, right? If we took the absolute value of a negative number, it would turn positive. Well, this basically just turns all areas positive. So let's look at what they want us to do. They want us to go from -2 to 1. I'm going to erase kind of what I have going on here so I can draw on it clearer. And let's see what happens. If I go from -2 to 1, now those bounds are correct because the lowest number is on the bottom. So I'm going to go here at -2 to 1. But now notice I got to split this up. And I got to find the area of this piece and this piece. However, this piece was negative. So what we're going to do is we're actually going to think of it visually as what happens if I flipped it up. Right? Really, that's what's happening is this area flips up and now becomes positive. Now, you don't have to visually draw that, but you can think of it that way. And then you just find the area of these two pieces. Well, this is a base of 2 and a height of 4. So if I wanted to set up the integral, I went from -2 to 0. And that area was a base of 2, height of 4, and that ends up being a positive 4. And then we had the other one that has a base of 1 and a height of 4. And that was the area from 0 to 1. Notice I cover the entire bounds. Eventually, I just split it up at 0. So then, it's 1/2 1 times 4, which is 2. And the answer here is a positive 6. Okay, now, we are going to teach you eventually how to do this in your calculator when you're given a function itself, not a graph. If you're given a graph, you have to rely on geometric area. Okay, well, this leads us into one of the questions that we had from the 6.3 day one. And what I noticed with some of the results is this problem specifically just gave us a little bit of a challenge. So I decided to do it here for you. This was from a couple days ago, last Thursday, Friday. And it was the problem that said you have a semicircle made up of linear pieces as well. And then we had to find the area under the curve from -8 to 7 of the function. So I split this up just kind of really quickly from -8 to -2. That's the red area here. Well, we can find that area by doing a triangle. So I did from -8 to -2. And then we have the little blue triangle right here. So from -2 to -1. And that's just a 1/2. So I did the areas over here. You can follow the work, but that gave me a 1/2. And the part that I think got people a little bit is notice this is a semicircle, but it's raised up. It's elevated by a rectangle that's a 1 by 8. So if I'm calculating the area underneath the curve from -1 to 7, I have to do the semicircle plus the rectangle below. So I do a 1 by 8, which is an 8 units here. And then the circle, pi r squared, cut in half because it's a semicircle. So we get 16, half of 16 is 8 pi. And then the answer here is 8 plus 8 pi. That represents the entire area under this curve. Okay, so then what I did after that was I just realized that I have a 1/2, so I changed everything to a 1/2, to a denominator of 2, added them up, and I got -19 halves plus 8 pi, or you might say -9.5 plus 8 pi. You could even turn this into 16 pi over 2, and then you could write it as -19 plus 16 pi, all divided by 2. So it's important to be able to kind of understand all three of these, because if this was a multiple choice question, you would have to be able to figure out which answer um, this came from, depending on the form it was given. So hopefully that helped to answer the question. I can see it was a little tricky because it just was raised up, it's elevated. But think of the integral as the amount of space that's covered between the curve and the x-axis. And if it's above the x-axis, it's positive. If it's below, it's negative. Okay. um, Today we're doing another day with the fundamental theorem of calculus. We are going to continue the part 2 fundamental theorem of calculus today, and then we're going to also include the part 1. And we did flip kind of the order that it's presented in your book, and I think for logical reasons you'll see that appear. So it's up to you if you want to write what I'm going to show you here. I just want to show you this really quick, is how did we do the integral? What was the fundamental theorem of calculus part 2, right? Well, all it said was if I have a function f of x, and I'm going to evaluate f of x from a to b, we do that by taking the antiderivative. And the way we represented the antiderivative was the capital F of x, right? So this was the antiderivative. And then we have the bounds from a to b, and we evaluate that. We evaluate it at b first, and then we subtract the bounds at a. So the big connection is how did we go from the lowercase f of x to the uppercase, and that was the antiderivative, which basically said we don't need a graph anymore because we know antiderivatives, and once I have the antiderivative, I can just evaluate it from the upper bound minus the lower bound. Now, the fundamental theorem of calculus part 1, the new part, I'm just going to share this with you, but it's you'll get the hang of it after a while. What if I take everything that I had right here? Okay, now I'm going to make one change, and actually maybe kind of two small changes. What if I put x here instead of b? So x is a variable. A is a constant. That's just a number. In this case, a and b were just constants. And then t, the reason why it changed from t, whoops, that should have an x. The reason why it changed to t is this is kind of like a dummy variable. So what would I do? I would take the antiderivative, and I'm not going to write this part, but I would do the capital F at x, and then subtract the capital F at a. So that's the same thing, right? So what's the new part? What is the part 1? Well, the part 1 is kind of simple. It says, what if I take the derivative of this entire thing? What does a derivative and an integral do? They cancel each other out, right? So you'll see that here in a second. But what if I take the derivative of, maybe I'll do it like this. What if I take the derivative of both sides? Well, if I end up taking the derivative of both sides, watch what happens. Now keep in mind, this is a variable, right? So this is just an x, but a is a number, right? So this is going to give me a constant of some type. We don't know what that constant is, but we know it's going to be a number. This will be an equation of some type. So what if I take the derivative of that? If I take the derivative of a capital F, I'm left with lowercase f. But then I do have to multiply by the derivative of the inside. So we have a little bit of a chain rule there, which we'll show you. But notice the other part. Since a is a constant, this whole number is a constant. The derivative of the constant is 0. And what's actually left over is f of x times the chain rule. Well, wait a minute. Couldn't we just figure that out right away? Notice this is a lowercase f, and this is also the lowercase f. Couldn't I have just taken this x and plugged it right in here to start and skipped all this work? And technically, yes. So if you didn't get that right now, this is more theory-based. I'll show you with the specific example, and you'll see exactly how and why this works. But those are the two things we're going to do today. All right. The first goal is to deal with more definite integrals and just give you a little more practice on this, because I think that these are challenging, and I know students really struggle with anything that's not just a friendly power rule. So we'll kind of do part of this together. There's going to be a piece where I just want to get you on the right start, and then I'll have you simplify it. So what do we have? We have to find the integral from 0 to 16 of the cube root of x plus 2 dx. Well, right now I don't make a strong connection to the fourth root of x the way it's written. So we have to remember, in calculus, our best friend is algebra. Right? Just like when we were doing derivatives, if you can find a better way to rewrite this, it's going to help you out a whole lot more. So remember, just the square root of x was equal to x to the 1/2. So if I put a fourth in front of that, a 4, it'll be x to the 1/4. So anytime you have an index number here, it really just goes in the reciprocal. All right? So I'm just rewriting this because now I can actually apply the reverse power rule. Right? So I want to take the antiderivative, which means we are going to add 1 to the exponent. Okay? So instead of adding 1 like this, what I'm going to do is I'm going to change that 1 to a better form of 1. We're going to add 4 over 4. That's still 1, but that helps me kind of identify. I get x to the 5/4. Now, as we talked about before, when you put an exponent up top, you want to divide by that number. But dividing by a fraction is not friendly, so instead we multiply by the reciprocal. That's really big, I think, in terms of just understanding. Does everyone kind of see where the 5/4 came from? And then if I put 5/4 in the exponent, to compensate for that when I take the derivative, I need something that would reduce out a 5/4, so I put the reciprocal 4/5 out in front. And then the last part is we think whose derivative gives me 2, and that's 2x. Now notice, one of the questions I often answer is, where did this integral sign go? Well, the act of taking the antiderivative is the integral. Where does the dx go? The dx is the difference between the upper bound and the lower bound. So that's where this line comes from, and we're now going to evaluate at 16 and at 0. The thing you have to be aware of is we always take the upper bound first, and it's going to go into the x wherever there's an x. In this case, we have 2 spots for that. Right? So we've got the upper bound, and I'm going to put 16 in for x in both spots. And then we're going to subtract whatever the lower bound is. The lower bound is at 0. and it will always be the upper minus lower. So that's the calculus side, right? That's technically, we're done with calculus right here. Everything else is just simplifying. And that's the part where actually most of the errors occur. So one of the really nice things is the zero, right? If you realize that when you plug zero into a polynomial, you do not have to do anything other than just say, you know what, this whole thing is going to be zero. Okay, and then most of the work is right here. Oops, this should be a 16. Thank you, Colin. Good catch. Sorry, 16 right there. Because 16 was going in for x. Okay. Now, what I've found students struggle with the most is this part right here. Because this would be a no calculator question for sure. So I might do a little side work over here and say, okay, well, what is 4/5 times 16 to the 5/4? How do we want to think of that? Well, the 4/5 is going to stay. I'm not going to do anything with that. But what I am going to do is I have an option. I could take 16 to the 5th power and then do the 4th root, which please don't do, because 16 to the 5th power without a calculator would be a nightmare. So I would do this. I would say, let's leave the 1/4 and pull the 5th power out. And then we know that the 1/4 is the same as 16 to the 4th power, or the 4th root, excuse me. And then the 4th root of 16 is what times itself gives me 16 4 times? Well, 2 times 2 times 2 times 2. So the 4th root of 16 is 2. And then 2 to the 15th power is 32. 2 to the 5th power is 32. And then I would put that over 1. And unfortunately, nothing reduces out, so then we just got to multiply straight across. And I'm thinking 4 times 30 is 120, and 4 times 2 is 8, so this will give me 128 up top, plus 5. 5 on the bottom. So all of that work, they do expect you to do without a calculator, and that's what this turns into. And then I know this is going to be 32, but I'm going to think of that as 32 over 1, and I want to make this so it has the same denominator. So we might as well times top and the bottom by 5, just so we can get same denominator, so we can add the numerators together. And 5 times 30 is 150. 5 times 2 is 10, so that'll give me 160. And then we can just keep the denominator and add the numerators to give me 288 over 5. So again, this would be something that you would probably see as a multiple choice question. And you would have to be able to do all of this work that we just talked about here to get to the answer that's presented without a calculator. Okay, so let's look at 2 more here. And these are both more tricky ones, and we're going to do, next week, we're going to do tricky ones as well. So they don't ever go away. We just become more comfortable with them. The absolute value one, right? This is a little bit tricky. And there's 2 ways we could think of this. The first way is if you realize that you could create a graph from this, from 0 to 5. So let's just put 5 out here. And what I'm going to do is I'm going to say, okay, well, what does this graph look like? Right? What if I plug 0 into the function? If I plug 0 in, I get 4 minus 0, which puts me up here at 4 roughly. And then if I plug 5 in, I get 4 minus 10, which is negative 6, but then the absolute value turns that into a positive 6. But then I have to realize that this is a V shape. So I kind of know that if I plug x equals 2 in, 2 times 2 is 4, 4 minus 4 is 0, so that will put me right here. And I know that every absolute value is going to look like a V. So if you know what this looks like graphically, then all you have to do is find the area of this triangle, add it to the area of this triangle, and that's your area. But what if we wanted to do this algebraically? And this is the weird part. We can do two different things, right? Notice the graph. I can split this up as one function and another. So what I'm going to actually do is say that this integral is actually equal to the integral from 0 to 2 of 4 minus 2x dx. Now, why did I not put the absolute value bars? Notice this is a negative linear equation, so its slope is going down. So that would represent this line right here. So the area under this curve is represented nicely by that shape. And then the second one is the integral from 2 to 5. But notice this is a positive slope, which means these values are going to be flipped around. So what I would do is I would take this as the opposite of what we have. And notice if I was to change that, this would be, I could pull the negative out or I could distribute the negative. And this should make sense. This has a linear equation that has a positive 2 for a slope and a negative 4. So negative 4 will be down here, and that would give me this line here, but I only want the area under the curve from 2 to 5. So what that means is I now can do this algebraically. Or I can use calculus. I can use the fundamental theorem of calculus to do this. So I'm going to basically use the antiderivatives here and evaluate. So I'm thinking, whose derivative gives me 4? That's 4x. Whose derivative gives me negative 2x to the first power? Well, that's a minus x squared because I add 1 up top. And if you're not sure on that answer, take the derivative of it, and do I get back to where I had originally? And then I have to evaluate that from 0 to 2. Okay, now this one has almost the same antiderivative. Whose derivative gives me negative 4? That's negative 4x. Whose derivative gives me positive 2x? That's x squared. And we go from 2 to 5. Okay, so again, this is just a quick review. And now we're going to evaluate from the upper bound, plugging in 2, minus the lower bound. Now, in this case, I know if I plug 0 in here and here, I don't have to write it out. You could just say that whole thing is going to be 0. But I will say you got to be really cautious, because if I had e to the x in there, e to the 0 power is not 0. Remember, anything to the 0 power is 1. So if you had like a 5 to the x and you plugged in 0, that's equal to 1. And a lot of students in my last hour are getting really confused on that. So I do this part with caution. The only reason why I put 0 here is I know that both of these are 0. Okay, so then we get 8 minus 4, which is just 4. So this whole thing turns into 4. And then we're going to do the same work here. We're going to plug in 5 to both spots. And then we have to plug in 2. Now notice how I put this in parentheses. Right? If I don't put parentheses around here, this negative does not get accounted for, and a lot of times that's where students make the error. It's the upper bound minus the entire lower bound. And then we can just quickly simplify. That's going to give me a total of positive 5 here, minus, this will be negative 8 plus 4, so that's minus 4. Those are going to turn into addition and give me 9. And I know the total answer, the total area under the curve of the original problem was 13. Okay? So just be careful. These problems occur every once in a while. I've seen them on like 1 or 2 AP tests, and that's it. Okay. I'd like you to write this one down right here, because this one really tends to get kids confused, and it looks scary. So we're going to get you to a point where you're going to feel hopefully pretty confident about it. We have the integral from 1 to 9 of this kind of crazy function. Well, as we learned before, algebra is your best friend. Before I do any calculus, we're going to rewrite this. Okay? And I'm going to do a couple of things here. The first thing I'm going to talk about is we don't like the square root of x. Right? We want to think of that as x to the 1/2. But I've got an x and a negative 2 that are both being divided by that. So what we're going to do is we're actually going to split this up as this x divided by its own x to the 1/2. And then we're going to subtract the 2, but the 2 also has to be divided by the x to the 1/2. And it's usually this step that students don't see. Once we have that, then we're actually able to do a little bit more simplifying, and then we can apply the power rule, the reverse power rule. All right, now one thing I'm going to do, this is officially x to the first power here, but I want to think of it as the power of x to the 2/2, right? That's still 1. It doesn't change anything. But what it does allow us to do is remember this rule. If I have x to the 7th over x to the 5th, our rule was to subtract those exponents. So I could call that x to the 2nd. So I'm going to do the same thing, it's just fractions. I'm going to subtract the upper exponent minus the lower. So I get base x, and 2/1 minus 1/2 is a positive 1/2. Okay? And then the next piece, we're okay with the way it's written, except for I don't love that this x to the 1/2 is in the denominator. So I'm going to bring it up in the numerator and call it negative 2x to the negative 1/2. All right. So now we have it algebraically rewritten, so we can actually do the calculus now. And we're undoing the power rule here. So what I'm going to do is add 1. Now notice that's that creative form of 1. So I'll get x to the 3/2 up top. 1/2 plus 2/2 is 3/2. But if I put a 3/2 up top, I have to put a 2/3 out in front. We're always multiplying by the reciprocal of whatever's in the exponent. Now some people like to just write this negative 2 here, which is fine. I'm going to leave a little bit of a space. And then I'm going to add 1 up top here. Right? That creative form of 1 is 2/2. So I get negative 1/2 plus 2/2, which is a positive 1/2 in the exponent. And if I put a positive 1/2 up there, I have to multiply by the reciprocal. And notice that's going to actually turn this into a negative 4. And then we used the integral symbol, so that integral symbol goes away. The dx is going to be the difference between the x's at 9 and 1. So now we just have to evaluate. We're going to plug 9 into both spots. And we know that -2 and 2, that's going to give me 4. So I'm going to simplify that piece here. And you could even write, instead of the 1/2, you could write that as the square root of 9 if you'd like. And then we're going to evaluate the lower bound as well. So 1 is going to go into both spots where the x occurs. Okay. What I'd like you to do is try to simplify this right now on your own. See how far you can get. Okay, so let's look at these. I'm going to deal with the 9 to the 3/2 first. And the first thing I'm going to say is, well, if I think of this as a 1/2, that 1/2 is the same as the square root. And then that'll be the square root of 9, which is 3. And 3 to the 3rd power is 27. So then that has to be multiplied by 2/3. And then the 3 and the 27, that's going to reduce out. So I'll have 2 times 9, which is 18. And then I'm going to do the same work here. The square root of 9 is the same as 9 to the 1/2. And that comes 4 times 3, so 12. So the first upper bounds reduces down to give me 6. Nothing special there. And then we're subtracting. Now this is kind of friendly because 1 to any power is always 1, so it's 2/3 minus 4. But I'm going to think of this as 4 over 1. So then I'll count that as 2/3. And instead of writing it as 4, I'm going to think of that as 12/3. 12/3 is the same as 4 over 1. And that allows me to subtract and get -10/3. And then all I'm going to do is change this to an 18 over 3. And we have subtraction of a negative, so that's going to be a positive. And my final answer is 28/3. As you can see, there's a lot of exponent work and fraction work mixed in within calculus. And you might not be super confident in your calculus skills or even your fraction and exponent skills, but I can tell you at the end of the year, you're going to look back and you're going to be like, holy cow, I've grown so much with all the extra practice that all your math skills are getting improved just by taking calculus. Okay. This one I don't want you to write. I just want you to see this one really quickly, and it's a unique one. Okay? Now, right away, this really confuses kids. And for every reason possible, it's got a square root. There's nothing really up top. Algebraically, it doesn't really help me to find this. The trick is we want to think right away, whose derivative gives me this? And if you have your derivative sheet in front of you, if you scroll down your list of derivatives, whose derivative gave me 1 over the square root of 1 minus x squared? Well, the antiderivative of this was arc sine or sine inverse. And then we're going to evaluate it at square root 3 over 2 and 0. So that's just the trick. This was an inverse trig, and we only, in AB calculus, we only need to know inverse sine and inverse tangent. If it was this, that's the inverse tangent one, and the one with the square root would be inverse sine. So that's really tricky. just being able to recognize that means you've mastered your derivatives, and you can go back to think of whose derivative would give you this as an answer. And then how do we evaluate this? There's more than one way, but I'm going to evaluate the upper bound minus the lower bound. And then I'm thinking, well, sine, whose ratio of sine gave me square root 3 over 2? If you're a unit circle person, we're thinking square root 3 over 2 is the y value. Remember, sine is always the y value, so that means I'm going to go up high at square root 3 over 2, and then, oops, that's the x value. The y value would be square root 3 over 2, which means the x value would be 1/2. And we're just thinking, whose angle gave me that? And that answer is this is a pi over 3. Right? It's a 60-degree chunk, so the answer to this is pi over 3. And then we're going to subtract whose value of sine gives me 0. Well, I know that we've got, at this spot, I go over 1 up 0, and the sine value is the y. And this spot, we go over 0 up 1. So what is it? It's 0 degrees. And the answer here is just pi over 3. So the reason why they would put a problem like this on is just to check if you know that antiderivative, and then can you evaluate inverse functions. There's other ways to do this. You could have done the opposite over hypotenuse and figure it out using special right triangles that it's pi over 3 as well. Okay, so this part is going to lead us into the new piece today. And we have a little bit to write down. You don't have to write down this part in black, but I would like you to write this part down here, the blue. And we're going to do this together because what we're going to do is we're going to evaluate the integral, and then we're going to take the derivative of it. Because our ultimate goal is to see what happens if I take the derivative of an integral. What happens? And I hinted at that earlier in class. But I think this will really help solidify what we're doing. So only write the blue. And we're just going to evaluate it. Right? What is y equal to? Right? Well, y is equal to the integral from from pi over 2 to x of 3 cosine dt. Now this 3 is a constant. We could, if we wanted, write the 3 on the outside. That's one of the properties we're going to talk about tomorrow, but we can just kind of leave that for now. So I'm thinking, well, wait a minute, whose derivative gives me cosine? Well, that answer is sine, right? The antiderivative of cosine is sine. The 3 is just going to stay in front. Now I'm going to call this t, because that's the variable that they had given us. That's really a dummy variable. It can be t, r, h, it doesn't matter. But what does matter is then I have to evaluate from the upper bound to the lower bound. Now we're just going to say this whole time, this is what y is equal to. So then what do? We found the antiderivative. We're going to take x first and plug it into the variable. So I'll get 3 sine of x. And then we're going to subtract the lower bound evaluated. So 3 sine of pi over 3. All right, well, we can't evaluate the x, so this first part is just 3 sine of x. And I can do this over here. What is sine at pi over 3? Now you have a couple of ways if you like the unit circle. We just kind of drew this out. Pi over 3 is the taller triangle. So I would go over 1/2 up square root 3 over 2. And that's in first quadrant. And sine is the y value. So, oh, sorry, man, I am screwing up. It's pi over 2. Thanks, Sydney. That's a pi over 2. Let me rewrite that. Okay, so we're plugging pi over 2 in, which is much easier to evaluate. So where's sine at pi over 2? 90 degrees. Go over 0, up 1. Sine is the y value. So this would be 3 times 1. So what does y equal to then? Well, y is equal to 3 sine of x minus 3 times 1, or 3. Right? Nothing special. This was the fundamental theorem of calculus part 2. Right? That just says take the antiderivative, evaluate at the upper bound minus the lower bound. Well, the new part today is what if I tell you to take the derivative of this integral? Okay, so let me see if I can do this creatively. What if I started at the very beginning, I told you to take d dx. Now you have two options. You can do all of this work that we just did, but then at the end, you take your derivative, right? And right now, that's probably what you would do. Kind of like order of operations. You do the inside part first, and then we still didn't take the derivative of any of this. So now, to find dy dx, now I have to take the derivative of the simplified inside. Well, the derivative of y is dy dx. And then I'm going to take the derivative of 3 sine of x. So the derivative of 3 sine of x is 3 cosine of x. And the derivative of the negative 3, because it's a constant, is 0. Now, if we had a lot more time, I would do 4 or 5 problems like this, and I'd have you work through all the antiderivatives and evaluate it, and then you take the derivative of your answer. But what we want to talk about today is the integral and the derivative. These two operations are inverse operations. It's like adding and then subtracting the same value. You get back to where you started, or multiplying and dividing, or square and square rooting. These are inverse operations. Look at our answer. Our answer is 3 cosine of x. Let's compare that to what we started with, 3 cosine of t. So really, what's the only thing that happened? We took the x value and we plugged it in right here. And that's where this x comes from. Now, there's a little bit more to it, because if this was something other than x, let's say it was a 2x, okay, watch what happens if this is a 2x. Please don't write this because I'm going to kind of erase it as we go along, but if this was a 2x, then I would have to put a 2x here, and then I'd get a 2x in here, right? So that would be a 2x in there, there'd be a 2x in here, and then when I take the derivative, I would have to do the chain rule, right? So then the chain rule would actually make another 2 come out right here. So if there's something more than x, we actually have to times by the derivative of the chain rule. And I'll show you that in a little bit. So what does this mean? This means that if you realize that they're asking you to take the derivative of an integral, you can say that these two reduce each other out, and you're taking whatever bound and plugging it in for the variable. Now, why did I not plug in pi over 2, right? How come I didn't plug pi over 2 in? Well, I did, right? That was this part, this part, this part, but look at, when I plug a number into the function, it's going to give me a constant. And the derivative of every constant is 0. So I don't care what this number is. The derivative of an integral, we don't care about that constant because it's going to be 0. We only care about the variable, in this case, 2x. Now there is one stipulation to this. The 2x, the variable, must be on top. If it's on bottom, notice it would be on this right-hand side, and that negative, because we do the upper bound minus the lower bound, it would be the opposite sign. So that negative comes into play if it's in the bottom, but we have a property that allows us to overcome that. So this is what it means in terms of math speak. And we kind of showed this already, so I don't think you need to write this down. What we just talked about, or what is on this slide, is just a fancy way of saying that the derivative and the integral are inverse operations. They cancel each other out. So here's what our book says. If we have a function, let's call it I, and I is the integral from x to a of a function f of t dt. And then I ask you to take the derivative of that integral. Notice, this derivative and this integral, they're going to cancel each other out, and what happens is the x goes into the function, and there's my answer. Why don't we deal with the a? Because a is a constant, and if I took the derivative of a constant, it would end up being 0. So some students like to think of, well, I could put a plus 0 at the end, but that doesn't really change anything. Okay? All right. We don't have to look at that. We already explained that. So now let's look at how fast this can be. Okay? Definitely write this down. We're going to do the shortcut here, and you'll see how quick your answer will appear. All right. Notice the directions. Find y prime, or another way we could write that is find dy dx. Right? So what I need to do is I need to take the derivative of both sides. And the derivative of the left side, that's where the dy dx comes into play. Right? Derivative of y is technically 1 dy dx, but we don't write the 1. Now we know that I could try to work through, and this is not very friendly, but I could try to work through the derivative, and I would get the upper bound of the antiderivative minus the lower bound at the antiderivative. But this lower bound is just a constant. So its derivative is going to be 0. And the derivative of an integral is just going to say, take this x value, and notice it's on top, so that's a good thing, and plug it in, and the derivative and the integral are going to reduce each other out, and all I'm left with is the exact function we started with times x. Now notice, it's not w, the x is going into place, and then I should write over here, it's times dx dx, because what's the derivative of dx dx? It's 1. Okay? But what if, instead of x, what if this was a 6? So we're going to rewrite this. What if this was a 6x? Well, what's going to go in here? 6x will go in here. Right? And then we have to times by the derivative of this. So the dx, derivative of 6x is 6. So if I change that to a 6, this would be my final answer. And it's all because the derivative and the integral are inverse operations. Sometimes students don't love this because it's a shortcut, and you really got to think about why it works to apply it. So let's try another one. Let's see how you feel about this one. Looks kind of scary. I've got the natural log of the sine of v dv, and they tell me to find y prime. But notice one thing. hopefully when you're reading this or when you're writing it down, you're thinking, I don't love this problem right now. And it's not because of the 5. Look at where that 5x is. That would officially be the lower bound. So we would have the upper bound minus the lower bound. And this part would be subtracting the lower bound. So I don't love that this 5x is here. What I do want to do is I want to rewrite this first. So what we're going to do is we're going to apply that one property we talked about the other day. That says you are allowed to flip the bounds. But if you flip the bounds, then that is going to result in the opposite sign of your answer. All right. So that's the first thing. And some students might want to write we flipped the bounds. Because you need the x to be on top when we apply this shortcut. So now that it's there, why don't you guys go ahead and see what your answer is? All right, so my goal is to find y prime or dy dx, which means I'm taking the derivative of both sides. And dy dx is the same as y prime. And then don't forget that this answer is going to be negative, right? Because we had to flip the bounds. And then the way my brain works is the dx and the integral are going to reduce each other out. And 5x, since it's not a constant, the 13 is a constant, so we don't have to worry about it. The 5x goes into the only spot where there's a variable. Now, if there were more than one v in this, we would have to plug it in everywhere. And we're left with the natural log of sine of 5x. Oops. Parentheses here. The natural log of sine. Oh yeah, there should be parentheses there. Because I want to put 5x where the v was. But notice, if I was to take my answer and do the derivative, there would be an extra 5 coming out. So we have to multiply the entire thing by 5. So that's the chain rule. And that's the one thing students forget about in a problem like this is it's really quick to just replace the 5x and the v, switch those. But they often forget about you have to apply the chain rule. And then my final answer, they would just write this 5 out in front. And just a reminder, the reason why we can do this is if 13 was plugged in and evaluated all the way through, at the end it would be a constant. And the derivative of the constant says the 13, when I take the derivative of it, is going to go away. It's going to be 0. Okay. We're going to save this one. So you won't come across this until we go over it. I just want to notice what happens if I have x's in the top and the bottom. We have to get a little creative with that, and we'll share that on Thursday or Friday for you guys. So here's what we got. Please make sure you understand what the expectations are today and then what we have for the rest of the week. So we've got our homework tonight is actually a quiz. It's in Schoology. You are going to have to submit a file upload problem, so please make sure you're showing your work for every problem. On Wednesday, you will be asked to watch an Edpuzzle video that introduces part of the lesson that we're going to do on Thursday, Friday, so make sure you watch that ahead of time. And then our test will be assigned next Thursday, Friday, and you're going to be given the weekend. And since we don't have school on Monday, February 15th, that will be President's Day. You'll have it'll be due on that Monday. So you'll have basically Thursday, Friday, Saturday, Sunday, Monday. You'll have 5 days to get that done. And since we're taking a test on that, any late work needs to be in by, I would say, next Wednesday for sure. So that way you can just focus on studying. That's all I have for today. If you have any questions, please stop into my office hours today. Otherwise, have a great day, and we'll see you Friday.